welcome to our lecture on rational inequalities. Real quickly, I would like to do a review of least common denominator. What we usually call LCD to abbreviate. Okay. So, for example, let's say I was looking at the following. Okay, let's say I was given the three following rational expressions. And let's say the instructions are to find the least common denominator. In order to do that, we just need to actually collect the factors of the bottom here. So let's find all the factors of the bottom. So over here we have one factor of x minus 2. Remember, it's not two separate factors, it's one factor, x minus 2. Here we have another factor, x plus 2. That's one factor. And here we've got x squared minus 4. So this actually can be reduced further. And how can we split that up? Well, right, difference of squares. So x minus 2, x plus 2. Great, okay, so let's look for the common factors that we have here. And we're going to collect as we go. So we're collecting factors as we go along. X minus 2, we've got x minus 2, so that's one factor that we've got. The next one, we move to the next one. Our factor here is x plus 2. I check in my sort of list that I have over here, and x plus 2 is not a factor yet that we have. We have x minus 2, but that's different from x plus 2, so we can collect this factor of x plus 2. Now I look at our next factor, and it's x minus 2, but I look back in my list that I've gotten already, and that's already in there, so we're good with that one. Our next factor is x plus 2. I look back at what I've got already, that's already in there as well, so we don't need to add it, and this is my LCD. Let's try another one. So let's say I've got 6 over x minus 3 and 8x squared over x squared minus 9. All right, so if I simplify this one so that we know what all of our factors are, we have, again, a difference of squares, right? 9 is a perfect square. So we can split this into x minus 3 and x plus 3. So what is the LCD here? Let's go along and look at what we've got. So we've got x minus 3 for the first one, so let's go ahead and collect that up. There's nothing in our list already, so that one does get included. Then let's move on to our second expression. We've got two factors. The first one is x minus 3. Well, we check our list, and we have that already, so that one's good to go. Now let's check the next one. We've got x plus 3. We don't have that one yet, so we have to add it. And that is my LCD here. Last example I want to bring up and 3 over x plus 2 squared. All right, so the first thing I want us to notice is what we can split this into. Well, we've got x plus 2 and x plus 2. So with this first one, we've got the first factor is x. So we've got LCD x. We don't have one of those yet, so let's include it. X plus 2 is our next factor here. We don't have an x plus 2 yet, so we can add x plus 2. Now let's move on to the next guy. We've got x plus 2 we need to check and see if we have that. Well, we've got one of those already, so that's good. But sort of the hang up here is that, what do I do with this guy? Do I just say, oh, I've already got that, and continue onward? We actually can't do that. Because this denominator has 2 factors of x plus 2, we have to add a second factor of x plus 2 here to account for both of them, right? So this one was already accounted for in our LCD, but this one was not, so we have to add a second. So that's our LCD. On top of that sort of refresher on least common denominator, I would like to do a quick review of polynomial inequalities. We worked on this before. Remember, we started out with quadratic inequalities, so polynomials of degree 2. And then we used the same technique to extend to polynomials. Let's say we've got this. So when doing these polynomial inequalities, our first step is that we would find all of the roots. Well, what are my roots here? It looks like I've got -2, 2, 2, and -1. Those are all my roots. So we want to put those on a number line, right? That's our whole deal with inequalities, is that we draw that number line. Remember, we are trying to keep track of where this function is positive or negative on this number line, right? We want to use these roots as sort of markers for where the function changes potentially from positive to negative. If we were to change from positive to negative, we would have to pass through 0. So we would have to pass through these roots. Let's get these written down here. So it looks like we've got -2, -1, and +2. What sort of points do we want to put on those? We want to put open points, right? Because we are looking for where we're strictly greater than, right? Not greater than or equal to. Because these are roots, it's where they pass through the x-axis. It's where the value of the function is 0. We don't want to include these, right? We don't want to be equal to 0. We want to be greater than, right? Not greater than or equal to, just greater than. So these are open. All right, so let's test these intervals. I would say the easiest point to test, right, that's less than -2 would probably be -3. If we plug that in, we get, for this one, -3 plus 2 is -1. -3 minus 2 gives me -5. Squared is +25. And then -3 plus 1 is -2. So it's negative times negative, so this one's going to be positive. Between -2 and -1, probably would test -1.5. -1.5 plus 2 is 0.5. -0.5 minus 2 is -3.5. If we square that, we get 12.25. And then -1.5 plus 1 gives me -0.5. So overall, I get just this negative times 2 positive. So this is going to end up being negative. Between -1 and 2, the easiest check would be 0. This is also x equals. I plug that in, I get 2. I plug that in here, I get 4. And I plug that in here, and I get 1. Right? All that is positive, so that'll be positive. And then, last but not least, let's say x equals 3. We get 3 plus 2, so 5. 3 minus 2, so 1 squared, which is 1. And 4, so this one is also positive. So since we are greater than 0, what do we want to shade these guys? How do we want to shade these guys? Remember, we're looking for greater than 0, so we want numbers that are positive specifically. So let's shade in the positive ones. Or, all right, we've got to now write this in interval notation. So we're starting from negative infinity, going all the way up to -2, but not including it. Starting again after -1, but not including it. Going all the way up to 2, but not including it. Skipping 2, starting again, just above 2, and continuing to infinity. So this is where this statement is true. Okay, so let's extend this technique for polynomial inequalities to rational functions. So I'm going to give y'all some quick guidelines. So rational function inequalities. These are some steps. So the very first thing is we want to make it look like those quadratic and polynomial inequalities. What did we always need to do? Very first thing. We always needed to set it equal to or unequal to 0, right? So we need to move everything to one side of the inequality. I squished it in, but that says inequality. 2, we want to use the LCD, the least common denominator, to combine into one fraction. We want to factor both the numerator and denominator. Four, this is where the familiar part comes in, so that's kind of just getting us all set up. Number line. With our number line before, we put down our roots of whatever we were dealing with, whether it was a quadratic or a polynomial. We're going to do the same thing. We're going to draw the roots of the denominator. And we're also going to draw the roots of the numerator. You'll see why I'm writing these both down separately in just a second. We want to think about whether we fill in the points, or leave them open. So what are roots of the denominator? When have we thought about that before? When we're looking for the domain of something, right? We need to look at the roots of the denominator when we're trying to find domain, because if we have something that is a root of the denominator, that means that's something that makes it 0, and a 0 in the denominator is undefined. Since we're undefined at the roots of our denominator, this is going to be always open. How could we tell whether a function is positive or negative, right? Whether it's greater than or not greater than 0, if it doesn't even exist. So these always have to be open. Now, roots of the numerator, whether those are included or not, are going to depend on our normal rules for these, right? So if we have greater than or equal to or less than or equal to, then we're going to have closed points, right, filled in. If it's greater than or less than, right, we don't want to include the points where we're equal to 0. In that case, it's open. I want to remind us that the reason that this is the case is because the roots of the numerator are where the function is equal to 0. 5. Back to normal steps of inequalities. 5, we want to test intervals between each root for their sign, positive or negative. 6, write the solution in interval notation. All right, so let's give it a shot real quick. I'm gonna do that right here. So our first example, let's say we're given x plus 2, x minus 1 over x plus 3 and x minus 3. Is greater than or equal to 0. Well, we've got a whole bunch of our steps done for us, right? Everything's moved to one side. It's all combined into one fraction. And both the numerator and denominator are factored. So the first thing we have to do here, we get to actually skip all the way to drawing the number line. So let's put our roots here. Looks like we've got one that's -3. Got one that's -2. Got one that's +1 and +3. So am I gonna use closed or open circles on these guys? Well, it's actually going to depend, right? So stuff from the denominator, remember, we want to leave not included, right? If something is a root of the denominator, that means if I plug in 3, or if I plug in -3, this will be 0, which means that this whole denominator will be 0, which means that this will be undefined. If it's undefined, I can't determine whether it's greater than or equal to 0 because it's just nothing, right? So this guy and this guy, the roots of the denominator, need to be open, right? It's definitely not going to be true at those points. Okay, so what about -2 and 1? So these guys are roots of the top. If I plug in -2, this will become 0, which means all this will be 0. But since this won't be 0, right, we don't have a repeated factor, since this won't be 0, then the top is 0, the whole fraction is equal to 0. So we have 0, which is greater than or equal to 0, right? It's equal to 0, greater than or equal to 0. So we want to include these guys, right? We have that greater than or equal to, right? The or equal to 0. So the places where we are equal to 0 are going to count. So we have all of our points here. So let's test some values. Let's say we test x equals -4. Let's say we test x equals -2.5, x equals 0, x equals 2, and maybe x equals 4. So why don't y'all take a second, pause it, and try to figure out these test intervals. So tell me whether these guys are positive or negative. Okay, so we've got this interesting sort of alternating pattern. Which one are we going to shade? Are we going to shade positives or negatives? Well, remember, we're looking for greater than or equal to, so stuff that's greater than or equal to is positive. So let's shade the positives here. And then in order to finish, right, we've got to give the solution in interval notation. So let's go ahead and do that. Looks like we're starting at -infinity. continuing up to -3, but not including it. Taking a break, starting again at -2, and yes, including it. Moving all the way up to 1, including it, starting at 3, and continuing up to infinity. So this is my answer. All right, let's say we're looking at number 1 here. So we've got this rational expression, but this time we've got a constant on the other side, right? We need it to be 0 over here. So we've actually got to bring this over. So let's go ahead and do that. So our first step would be to bring everything over to one side. Greater than 0. In order to combine these, what am I going to do? I need to have a common denominator, right? In order to add and subtract fractions, I have to have a common denominator. So we have got to find the least common denominator. So looks like I've got 1 factor of x plus 2. What is the denominator of this? Is it 0? Nope, it's not going to be 0, right? If I've got something with no denominator, then the implied denominator is 1. So x plus 2 times 1 is just x plus 2. So that's all my least common denominator is, which is great news for us. How do I use this to do this combining? Well, now I've got 2x minus 1 over x plus 2. How can I change this minus 1 to have that common denominator? We have to do something that doesn't change it, right? So things that don't change something are adding by 0 or multiplying by 1, right? So is there a way that I could multiply 1 by 1 but make it look like this, make it have the least common denominator we need? There is, right? If I multiply by x plus 2 over x plus 2, then I've got the denominator I want, right? I multiply across the top, right? So 1 times this. So all of this is greater than 0. I'm left with 2x minus 1 over x plus 2 minus, right? 1 times x plus 2 is just x plus 2 over x plus 2. All of that's still greater than 0. Now that I have the same denominator for both of these, I can just subtract them, right? So across the top, we've got 2x minus 1 minus x plus 2. I'm putting parentheses around this, right? Because this negative is applied to all of the stuff up here, right? We have to apply this negative to both of these terms. So I'm combining these so I can write them over the common denominator. We're still greater than or equal to 0 here. Now let's do this combining. So remember, this negative is going to apply to both here. We have to distribute it. So we've got 2x minus 1 minus x minus 2 over x plus 2. We want all that to be greater than 0. We combine like terms here. We get just 1x and then minus 3. Over x plus 2. So that actually simplified nicely. So let's draw our roots here on the number line. Roots of the top are what? Just positive 3. And roots of the denominator are just negative 2. That's all we've got. Now we know that this negative 2 is going to be open, right? We're going to have an open point because it's in the denominator, right? It's not included in our domain. X minus 3, that gives us this root of 3, right? If this is 0, then this whole thing is 0, right? If this is a root of the top, the whole value of the rational function is 0. 0 is not greater than 0, right? 0 is equal to 0. So since we have this greater than sign, this also needs to be not included. I test the points here. if I test these intervals, I get positive, negative, positive. What am I going to shade here? We've got greater than, so positive. Positive is greater than 0. Okay, so what is this in interval notation? Negative infinity to negative 2, union 3 to infinity. And that's the answer. All right, let's figure out this next one down here. So with this guy, we've got everything on one side, and it's in one fraction, but the numerator and denominator are not factored. So we've got to do that before we can continue. So let's factor the top. So if I factor this numerator, I get x minus 5x plus 2. And if I factor the denominator, I get x plus 4, x minus 2. And I want all this to be less than or equal to 0. Okay, so what are the roots of this? All of the roots. We've got positive 5, negative 2, negative 4, and positive 2. So negative 4, negative 2, positive 2, positive 5. All right, what should I test? I'm just picking the smallest numbers. Well, if we test negative 5, we get negative times a negative times a negative times a negative. So 4 negatives is positive, right? An even number of negatives is positive. If I test negative 3, I get negative, negative, positive, negative. So that's 3 negatives. So that's a negative, right? Odd number of negatives is a negative. If I test 0, I get negative, positive, positive, negative. So 2 negatives. So we get positive. And if I do the same thing for these guys, I get negative, positive. Let's figure out what our points are going to look like. So this negative 4 is coming from where? The top or the bottom? The bottom. So stuff that comes from underneath, we leave open. So same goes for positive 2. The next root is negative 2, which came from up top, right? So the function is equal to 0 here. So since we want to be less than or equal to 0, we can include it. So same with positive 5. Okay, now am I shading the positives or negatives in this situation? We're looking for where we're less than or equal to 0, so negative numbers. We shade those in. Our solution interval starts at negative 4, not including it, continues to negative 2, including it, starts at positive 2, not including it, and ends at 5, including it. That's what we've got here. So we're looking at this guy. So I've got 4x plus 1 over x minus 2 is less than or equal to negative 2. So I bring this negative 2 over so that we have 0 over here. So we've got 4x plus 1 over x minus 2. We're bringing the 2 over, so it's plus 2 is less than or equal to 0. So now we want to have the same denominator here, right? Have a common denominator. So our LCD in this situation, well, we look at the first term. We've got a factor of x minus 2, so that's included. And then, like we said before, so if we bring over a constant, what do we have in the denominator? we have 1 in the denominator, right? So our LCD is just whatever factors we have times 1. So it's just that factor. So then we can multiply by a fraction, right, that is that factor over itself, right, the least common denominator, right? This cancels out to give me 1. And then we're multiplying 2 by 1, which doesn't change it at all. So we've got the denominator that we need and also haven't changed the expression. So let's multiply through here. And we can now combine because we have the same denominator. All right, let's simplify here. So we've got 4x plus 1 plus, so this 2 will distribute to both the x and the negative 2, so we get 2x minus 4. And all of this can be divided by x minus 2. We combine these like terms, we get 6x minus 3, all divided by x minus 2. All this is still less than or equal to 0. Okay, what are my roots here? Well, if we look at the top, right, we want to figure out where this is equal to 0, right, to find the root. So let's bring this 3 over. Looks like x is going to be, we divide by 6, we get 1/2. So it looks like my roots are 2 and 1/2. So let's put these guys on a number line. So what kind of points are we going to put on these guys? So let's look at 1/2 first. So that one's the top. If the top is 0, that means the whole fraction is 0. So we are less than or equal to 0. Yes, that's true, right? 0 is equal to 0, so we want to include this. 2, if I plug in 2, I get a 0 in the denominator. We don't want that, right? That's not included in our domain, so that's going to be open. Well, I'll spoil it for you. You get positive, negative, positive. And then since we're looking for where we're less than or equal to 0, we shade in the negative. That means we have the interval 1/2 to 2. All right, I want to do number 6 really quick. So let's subtract over. I look for the LCD. Look at this first term. We need to add all of the factors. Look at the second term. That's not included already, so we add that one in. So we want to have this least common denominator on both of these fractions. So for this first one, what are we missing? Looks like we're missing a factor of x minus 2, right? So we can multiply by x minus 2 over x minus 2. Then I'm subtracting this next term. What is this next term missing? Well, this one has the x minus 2, so it's actually missing the x plus 2. So I can multiply this by x plus 2 times x plus 2. We're still greater than 0. We're still looking for where it's greater than 0. We do this multiplication. We get 21 times x minus 2 over x plus 2 times x minus 2. And then subtract 3 times x plus 2 over x plus 2 times x minus 2. All right, now that we have the same denominator, even if these factors were flipped, it would still be the same denominator, right? We can flip multiplication and it doesn't change anything. So I've got the same denominators here. So now I can combine. So I end up with 21x minus 2 minus 3 times x plus 2 over same denominator. So I've combined the fractions now. So 21 we want to distribute, so we get 21x minus 2 times 21 is 42. And then minus 3 times x, so minus 3x minus 6. All over same denominator. I combine like terms, I get 18x minus 48 over this stuff. I've got to find the roots of the top and the bottom. Well, let's look at the top. So where is this equal to 0? Well, 18x minus 48 equals 0. We add the 48 over. We divide by 18. We get x equals 8 over 3. So let's go ahead and put this on the number line. We've got 3 roots here, so we've got -2, +2, and 8/3. Right, 8/3 is just a little bit larger than 2. So are we going to have closed or open points for these? Well, if I look at the positive and -2, right, those guys are where the function's undefined, so those are open. And then 8/3 would give us 0 on top, which would give us 0 for the value of the function. And 0 is not greater than itself, so this is also not included. I test the points in between. So if I test these guys, if I plug in -3 here, so I get -102 over -3 plus 2 is -1. -3 minus 2 is -5. So negative divided by 2 negative, so this is going to be negative. I test here, maybe 0. I get -48 over 2 times -2. So that's 2 negative, so that's positive. Between 2 and 8/3, I can choose maybe x equals 2.5. Then I get -3 over 2.5 plus 2 is 4.5. 2.5 minus 2 is just 0.5. So if I multiply all these together, we have a negative. And then if I test 3, I get over 3 times 3 plus 2 is 5, 3 minus 2 is 1. All of those are positives, so we get a positive. I want to shade in the positives because we're looking for where we're greater than 0. For our interval notation, looks like we're going to get -2 to +2, and then 8/3 to infinity. So that is my solution here. Last but not least that I wanted to cover really quickly was just this guy. It should be pretty short and sweet because we have everything across from 0. It's all in one function and it's factored for us already. So let's go ahead and look at this guy. If I look at the roots here, I've got 1 root of -4. I've got 1 root of 0, and I've got 1 root of 2. I've got a open point on -4, right, because that's in the denominator. I've got a closed point on the other 2 because we're greater than or equal to. All right, if I test here, if I test -5, I get positive, negative, negative. So I end up with a positive. If I test maybe -1 here. I get positive, negative, positive. So just one negative means we've got a negative, right? Odd number of negatives means a negative. Let's do x equals +1. I've got positive, negative, positive. So this is negative again because it's just one negative. And then x equals 3. I get positive, positive, positive. So this is positive. Now, which ones do I shade? The positives, right? Because that's where we're greater than or equal to 0. So now, what is my interval notation here? Well, I want to start at -5. So this is actually a mistake. I didn't mean to say -5. It actually should have been, if you look at the number line, should have been -infinity to -4. Continue on to -4, parenthesis, right? Don't want to include it. Now, do I start up again at 2? Are there any points that I would have missed if I skip all the way to 2? Yeah, right, I will have skipped this 0, right? It's filled in, so we need to include it. The way we include something that's on its own, right, it's not a part of an interval, we do that by using these curly brackets. Then we start up again at 2 and continue to infinity. That's this guy. Okay, that's all I had on rational inequalities. Let me know if you guys have any questions, and I will see you next time.